Hi everyone, and welcome back to the Blemmings Labs room. I'm delighted to introduce now Christopher Biggs to talk to you about Linux and Zephyr, sitting in a tree, literally. Christopher has been into open systems since the early 90s and was there pitching in at the birth of Linux and 386 BSD. His interest in electronics and connected devices goes back even further. Christopher's career encompasses software development, system architecture, and engineering management. Christopher is now the principal of Accelerando Consulting, a boutique consultancy focused on the Internet of Things, doing truly full-stack Linux from chips to cloud. Christopher is convener of the Brisbane Internet of Things interest group and was a founding member of Humbug, the Brisbane Open Systems user group. He's presented at conferences and user groups around Australia and internationally. In his spare time, he builds and blogs about robots with his 3 children and adds to the growing Internet of Things community. Thank you so much. Welcome, Christopher, and over to you.
Thank you, Pia. So my name's Christopher, and I'm here in sunny online from my home port of Brisbane, where I do run that consultancy called Accelerando. And what we do is we help people build the right technology faster. And we found over the last 5 years that while every problem is different, we do find ourselves reaching for the same tools over and over again. And after seeing several presentations about Zephyr at a number of previous LCA events, about 6 months ago, we decided to add Zephyr to our toolbox after looking at a number of options that occupy similar niches. Now, I'm not involved in the Zephyr project yet, so this is going to be my outsider's perspective on why we chose it and what techniques we've adopted to fit it into our processes. And this isn't really going to be an introduction to Zephyr itself, because project member Kate Stewart has done a number of good talks on that at LCA in recent years. So what I'm going to do is touch on what I see as the highlights and talk about some areas where you might get stuck. And I'd also like to give massive thanks to Lemore Freed and her keynote this morning. As has been the case every time I've spoken at LCA, the keynote speakers do a fabulous job of introducing everyone to the key topics that the later speakers will go deeper into. And this time I hope that you've all learned what a microcontroller is, and that there's a range of options from cheap and simple to still pretty cheap but more complex. And to add to what Lemore said, I want to talk about why we use technology, and in particular the so-called Internet of Things. For me, it's about because besides saving labour, technology lets us see further and do more, extending our conscious sphere beyond our mere bodies. So what is it like to be a thing on the internet? Well, presumably you've got a job to do, some reason why we built you. But that's really only 1/3 of the bigger picture. The other parts are cooperation and safety. The promise of IoT is that from a number of small parts, we get an overall picture that exceeds the sum of those parts. But with that ubiquity comes some risks, and we need to be aware that the chance exists that our creations can be turned to the dark side. And one of the ways we manage that risk is to avoid unnecessary complexity. And to demonstrate what I mean, we're all here at a virtual conference. We're all sitting in front of powerful computers, multitasking, the computer's multitasking. So what's wrong with that? Well, it's complexity and unpredictability. You've probably been in an event where somebody gets a mail notification or a instant message notification pop up in the middle of their presentation. And another reason why we might not want a general purpose computer is power usage. It's always a problem with the batteries. Imagine encasing your PC in concrete and just leaving the mouse cable sticking out. How long would it be until you regretted that? You buy some new game, you need to upgrade your video card. You install some new program, you need a bigger hard drive. So to get back to what Lemore said this morning, there's a spectrum of complexity, from single board computers that can run Linux just like any other general purpose computer, down to tiny little microcontrollers with no room for anything at all besides your application code. But in the middle, we have those systems on a chip, like the ESP32 that's in your swag badge, the NRF51 that Lemore spoke about, and a bunch of other chips that run at something near a few hundred megahertz. They have tens or hundreds of kilobytes of RAM. They maybe have a megabyte or flash memory. They're too small for Linux, but they can do significant work. some of these devices you can fit Linux on, like our home internet routers and many IoT security cameras. And oddly enough, that's where most of the horror stories about how the S in IoT stands for security come from. It's not that Linux is by nature insecure, so much that developers can lose focus and forget to clean up after their development shortcuts. So what if we made a small operating system that made it harder to screw up? Some other reasons why we might not want Linux or Windows or Android or macOS on our embedded devices is that they need a lot of storage, a lot of battery capacity. You're forever applying updates and cleaning out your hard drive when it fills up. There's a tendency to pop up a full screen dialog box asking, would you like to leave a product review, just as you were in the middle of landing your spaceship or giving a presentation. So taking those previous drawbacks in the opposite order, what if we invent the opposite kind of system? It's monomaniacally focused on doing just a few things. It can be expected to run for a long time without needing maintenance, and hopefully it can have a battery life measured in years instead of hours. So what's out there in that space? Well, you can cut down Linux and add a real-time scheduling underkernel. You can also choose from a number of commercial real-time operating systems that aren't too much unlike Linux, or you can use whatever proprietary code your chip vendor provides, or you can use another of the open real-time operating systems like NbIoT or the free RTOS, which is running on your conference page. And then there's Zephyr. I wouldn't say there's anything particularly revolutionary about it, but what we've found is it's a nice well-rounded package which appropriately ticks my boxes of free, flexible, and friendly. Some of the other things that drew me to Zephyr were its association with the Linux Foundation, its support for a wide number of chips, which gives me the option to change silicon vendors if I need to. It's pretty easy to add support for new boards without needing to wait for updates. It's got a lot of features and examples that cover common use cases. Security and quality appears to be a focus of the development, and it's a lot more convenient to debug and test than some of the other options. So let's look a little bit at that hardware support. It runs on most of the major chip families in use for IoT, including most of the recent Arduino boards, which means it is an excellent choice for those who find themselves outgrowing the Arduino ecosystem. It runs on the ESP32 processor that you'll find in your conference swag badge. It supports a heck ton of different sensors right out of the box, and it is pretty easy to write drivers for a new sensor when you need to. I would say that it doesn't support as many LCD screens as I'd like at the moment, but I found that the Bluetooth stack is good and small, and that's a key thing because with some other operating systems like FreeRTOS on the ESP32, you've got Bluetooth there, but once you start using the code, you find that it's so huge that you lose the ability to do software updates because you haven't got enough leftover flash memory. Another thing that drew us to Zephyr is that it's not opinionated about development tools. You can keep using your favorite IDE, and there aren't any black box vendor code blobs that you have to blindly trust. Look, I said I wasn't giving a complete introduction to Zephyr, so I'll cut this short and say that if you need a particular protocol or interface, you'll probably find that it's already there. And I am pleased as punch that Nordic and other vendors have said, you know what, we're going to stop foisting our proprietary stack on you and just ship Zephyr for our new chips. A number of the major vendors are financially supporting the Zephyr project. Adafruit, for example, Limor's company, are a Silver Zephyr Foundation member. The development process is appropriately open and releases are regular, and the documentation is great. What's not to like? So, how do you get started? Just read the fine manual. Seriously, the Getting Started guide is really good. It's so good that I only gave up in frustration twice before I finally got Zephyr working, and that's way less than every other OS I've met. So you want to start. I seem to have lost synchronization on my slides here. So you want to start coding for Zephyr. The compilers for different chips are mostly derived from the GNU compiler collection. The build system is CMake, and there's a Python wrapper that drives CMake for you, and installing all that stuff is only 4 steps. And after that, building an application is 1 line to build it and 1 line to install it on your microcontroller. I can't really overstress how refreshing all that is. Does it run on a Raspberry Pi? Well, yes and no. You can run your Zephyr application as a process on your PC, on your Linux box or your Mac or Windows, but Zephyr isn't really competing with Linux or other general purpose operating systems in that size range. It's targeting smaller systems that do less and have lesser resources. Can you develop for Zephyr on a Raspberry Pi? Well, if you follow the standard installation instructions, you can't. The compilers aren't packaged for Zephyr by Zephyr for the ARM-based Linux systems at this time. But you can do it, and I'm going to tell you how and why I set out to do that in the first place. First, the why. I've got a nice grunty MacBook which compiles my Zephyr OS in a few seconds. Why do I want to do that on a less powerful system instead? Most of the chips I work with are programmed over USB. Working on a Mac, I'm already in dongle hell, and I don't really want more cables holding my laptop down. Also, some of those USB chips that we use to interface to the serial ports of microcontrollers have slightly sketchy drivers for Mac and Windows that occasionally result in you needing to reboot your system, and that irritates me. So the compromise I've chosen is to have the code on my laptop, but to plug the cables into another system. And the 2 reasons why that works for me is, firstly, I can set up a test rig wherever it needs to be, maybe outside near the street, or next to a noisy piece of machinery, or up on the roof or down a hole. Meanwhile, I can be back in my office working in comfort. And secondly, at Accelerando, we've been trying to bring embedded development out of the 1980s by using source control and continuous integration and deployment pipelines like grown-up software engineers ought to. So if it isn't officially supported, can we get Zephyr onto a Raspberry Pi? Well, firstly, I haven't tried this for every chip that Zephyr supports. I mostly work with ARM processors and with the ESP32, and this definitely applies to all of them. Although Zephyr doesn't provide a compiler package for the Raspberry Pi, the GCC port for ARM processors is provided in a nice compiled package by the GCC project team, and Espressif do provide an ARM compiled version of their compilers. And as Lenore showed this morning, Python runs on pretty much everything. So all the parts are there, and we can largely follow those instruction processes. The one gotcha, if you're going to do this the way I did, you want to go out and get a Raspberry Pi with at least 4 gig of RAM. One of the Python libraries that Zephyr needs apparently has some components that are implemented in Rust, and I found that on an older Raspberry Pi with only 1 gig of memory, that step in the installation causes the system to pretty much grind to a standstill because the Rust compiler attempts to consume all available memory. I'm sure you could work around this, but I'm not really a Python extension building guru, so I haven't figured that one out yet. So the TLDR for how and why to get Zephyr on a Raspberry Pi is you want to install Ubuntu rather than the standard Raspberry OS because it's got more of the compilers that you're going to need already in the distro. So that's a little bit less to worry about. You want to have plenty of RAM, And for the rest of the steps, I've written a collection of salt stack rules which will install the components in the right order based on a combination of the Zephyr installation instructions and my own experiments. And I'll be making those available in a link at the end of this presentation. So let's talk about, for those of you who are not heavily into embedded systems but are now looking down at a badge hanging around your neck that you could potentially run Zephyr on, how do we work with hardware using Zephyr? Zephyr supports a number of different chip families, about 7 of them, and about 200 different individual circuit boards which contain typically a chip from one of those families, perhaps some extra memory, and maybe some peripherals like buttons and lights and interfaces to outside stuff. So if you look in the Zephyr source tree, under boards, under the type of processor, you'll probably find the name of the board that you have. And I'll talk later about some ones that I recommend if you want to go out and buy, which ones are good. And I'll also talk later in this presentation about how to add a new board if you've got one which is not yet supported. So as I said, that building process of essentially building the kernel and your application code into one big binary that you're going to copy over onto the device is pretty much one line. And the first time you run it, it's going to take a couple of minutes while it goes through and compiles about 300 steps of the guts of the operating system. And then the next time you do it, having changed your application, there's only a handful of files that will have changed, and it's super fast. And then so once you've got your compiled binary, you're going to copy it somehow onto your device, and the building and packaging tool takes care of that for you, because when you define a board, you define how that particular board is programmed, and typically that takes 30 seconds or so to copy the data across to the device. And that can be by a number of different mechanisms. You have, as Lamore mentioned this morning, some of the latest generation of boards just appear as a storage device, and you just drop your file on the board and away you go. Many of them, including the ESP, appear as a serial device, and you're talking to a small bootloader program which runs first before it starts your application. There's an interface called JTAG, which is a standard way to talk to microcontrollers. And there's another interface called single wire debug, which is also a standard of some kind, regardless of not actually being single wire. And they're all pretty seamless, and I'll go into some details and show you some examples of those in just a bit. I do want to stop briefly to rant about how awful microcontroller development tools are and have always been. It's a different world than open systems and commodity PC software. The volumes are smaller, the quality bar perhaps is not as high. There's I think never been a user experience person seen in the halls of any of the major chip vendors. So your options for development tools can be buying the official development kit from the chip vendor, which could cost you some hundreds of dollars. You might buy a programming tool from a cable from a programming tool vendor, and some of them are reasonably priced, and some of them are what I would consider unreasonably priced. You can buy unofficial clones of many of the more expensive commercial tools, or you can buy or build an open source programming tool. So in the buy column, if you're working with Nordic semiconductor chips, you're probably going to want something that is either a genuine Sega J-Link tool or something that has equivalent capabilities. And I was quite surprised to find that although for educational and non-commercial use they're under $100, the price for a commercial license is something like €600, about $1,000. There's another well-regarded tool from TI called the ST-Link, which is $20. Obviously a much better option. It does lack a couple of the capabilities that you may run into needing. And then there are unofficial clones of both of those devices. So here's a $5 clone of the Sega J-Link, which can work with the official software, but also works with some open source tools. Here's again a cheap and cheerful clone of the ST-Link, and there are options to replace the firmware in those with open firmware that you have complete visibility of. On the build side of the coin, there's a program called OpenOCD, which is used to control all of these little programming cables, but it can also use the general purpose input-output pins on a Raspberry Pi as an ersatz programming cable. So you can just use your Raspberry Pi as a programming cable. You can use OpenOCD, as I said, to drive these devices. You can buy a board called a Blackmagic debugger, which is a fully open equivalent. Or you can put some open source firmware either onto one of these boards, or you can just get a generic microcontroller board, costs a couple of dollars, and burn some firmware onto that, which will turn it into a USB programming cable. So once again, if you're working on your workstation under one of the supported platforms, your command to copy the software onto your device is just west flash, and it takes care of doing whatever's necessary, invoking the ST-Link or the J-Link tools or whatever to suit that particular board. If you're going to do it via a Raspberry Pi, we're going to be using an open source software package called OpenOCD, which just supports doing debugging and software installation for a number of microcontroller chips. And so the first step is we want to get our code onto our Raspberry Pi. So if you're compiling on your workstation, then you're going to want to copy across the Zephyr.hex file that comes out the end of that build process. Alternatively, you could keep all your source code on your Raspberry Pi and use remote editing from your workstation and build it directly on the Pi. It's fast enough that that's a valid option. Now, secondly, we're going to use OpenOCD to program the board, and that's going to depend on which particular programming cable you're using. These are some examples of what you would do if you were using a J-Link cable or an ST-Link cable. The command language of OpenOCD, like a number of open source tools, is extremely powerful, very flexibly scriptable, and pretty much impossible to learn from a standing start. So it's probably the distillation of a week or two of hair pulling here on this single slide of figuring out just what the magic incantation is to get everything to do its job. So I'm going to talk now about some more of the things that I think I can tell you that will save you some days of hair pulling. The documentation for Zephyr is, in general, very excellent, and I have nothing but praise for them. But these are the bits I've found where perhaps it doesn't go into quite enough detail to make it clear how to things to hang together. So firstly, you'll come across a concept called a device tree. And this is a mechanism invented by the folks at ARM for describing what resources are present in a computer. Now, if you think about your PC, for those of you like me who first encountered PCs in the 80s and the 90s, the way that they typically determined what hardware was plugged into their expansion slots was just to try and probe everything and see whether anything answers, which often led to bizarre side effects and crashes and all sorts of stuff, and also makes the operating systems huge because they have to have drivers for every product under the sun already present. Now today we have technologies like ACPI and PCI, which are low-level components in the BIOS of your computer and the hardware, which allow the expansion devices to identify themselves, so that the computer simply has to ask, well, hey, who's present on this bus? And the answers come back. So ARM invented device tree as a way to have an operating system image explain to the CPU what devices are going to be present. And so it describes what inputs and outputs that the boards has. For example, are there buttons? Are there lights? Is there a communication interface of a certain kind? Serial ports, I2C buses, SPI buses? Is there a screen somewhere? Do you have a microphone? All that information is going to be encoded in the device tree, and that's in most cases provided by the board definition. So if you've got a particular circuit board, here's one from SparkFun. It has a couple of lights and a couple of buttons and a battery and an I2C port for plugging in sensors. And so the location of all those devices, as into which pin they're connected to on the CPU, is described in the device tree document that is in the board subdirectory for that particular board. So from the point of view of my program, for example, the first program you're probably going to run is a simple little program called Blinky, which just blinks an LED. So my Zephyr software can say, give me the resource for LED 0. And it doesn't matter what pin it's on. It doesn't matter whether it's you set a 1 to turn it on or you set a 1 to turn it off. The device tree takes care of abstracting that, and I can just say, give me LED 1 and deal with it at that level. And the device tree can also be extended by your application, because you might have your existing board and then you might have some kind of sensor that you plug into it over a cable, and you want to explain to the CPU what pins this external sensor is plugged into. And so you can add what's called an overlay to the device tree to describe the particular things that your application is going to expect to find plugged in. So when you're building an application, and by that I mean the combination of the Zephyr kernel and your application code, you're going to configure the kernel to provide certain resources. And for those of you who are Linux kernel people, the Linux kernel is configured by a big text configuration file, which can also be edited via a menu system or via even a GUI program. And Zephyr actually uses the same system. So if you're familiar with make menu config in the context of the Linux kernel, you'll find exactly the same software being used to configure the Zephyr kernel. And so if you want to get a sort of a cook's tour of what Zephyr can do, you can run make menu config and then just squirrel through all those menus and go, oh gee, it's got this, oh it's got that, oh it can do that, oh there's an option for this. But in practice, don't, because it's huge and you might not know what you're doing. Sometimes you don't need to go into that level of detail. There might be 6 or 7 parameters that affect a particular peripheral, but really you don't need to mess with any more than one of them to configure it. So the way that I generally approach building a new application is I look for one of the sample applications that is relatively close, and I nick its configuration file and start from that. And then I might take a copy of that configuration file, run the menu config, and then compute the difference between those two files using diff, and that'll tell me what directives I need to put in my configuration file. I can also, if I'm building an application that's going to run on many different boards, I can provide different kernel configurations for different boards and even different device tree overlays, because I might have my sensor plugged into port 21 on this SparkFun board, but it might be on port 52 on this Nordic board. And those custom board definitions and custom device drivers and custom overlays, you can put them in the Zephyr source tree, or you can have your application completely outside the Zephyr source tree. Both of those are valid options, and it depends whether you're more comfortable working with a mono repo or with a one repo for the kernel and one repo for your application, or even using Git submodules, the horror. So practically, I do lean heavily on those sample applications. Here is a quick shell snippet of what I would typically do to build my configuration file. Is I start from an example that's sort of close enough in that it talks to the same kind of sensors, or it uses the same kind of interfaces. Then I run the menu config. Then I diff the before and after of that config and massage that output into my configuration file. But what if your board that you're using isn't supported at all? If the chip that you're using isn't supported, then you're going to be porting Zephyr to a new chip architecture, and that's a larger problem than a beginner might want to encounter. But if the chip's already supported, like here's a SparkFun board that uses the Nordic NRF52, there are other SparkFun boards that are supported by Zephyr, but this one wasn't. So what I did was I went into the Zephyr source tree and went, oh gee, there's an Adafruit board that uses the same variant of the NRF52 chip. So I grabbed that one and I looked through the documentation for both and figured out which pins the LEDs were connected to and which pins the I2C port was on, and produced a board definition for this file. Took me a couple of hours, worked pretty well, and that was something that I did within the first couple of weeks of learning Zephyr. And once you get an understanding of how device tree works, you'll find it pretty easy to add support for new boards that are not supported. In fact, I've designed and built a couple of development boards of my own design, which I've added support to Zephyr for. And on the application side, again, you want to do something. You want to read some sensor. You want to control some sort of network interface. There's hundreds, literally, of sample applications in the Zephyr tree, which also, in many cases, contribute to the test suite of Zephyr. And it's pretty easy to take a copy of that sample. It's literally a case of just copying the subdirectory out into your working area, and you've got a project which can be the nucleus of your new application. And if you've got a device which is not supported, say you've got some new model of motion sensor or new model of sensor, and here's an example of a board that uses a magnetic sensor that was not supported by Zephyr. You find a driver for a similar kind of sensor and basically monkey see, monkey do, and it's pretty easy to create a new driver, which you can either keep in your application tree or you can keep in the Zephyr source tree. And so at the moment I'm because I'm using these same chips and sensors across a number of projects, I'm actually maintaining a fork of Zephyr which has my boards and my sensors added on, and I simply rebase my branch onto the latest version of Zephyr every time Zephyr updates. Sometimes there are changes which break my code, and that takes half a day or so to sort it out, but in general that works pretty well. And one day when I have leisure, I will see about contributing those changes back to the Zephyr project. So what kinds of things did I get done in the first few weeks of learning how to work with Zephyr? As I said, I added support for a couple of basic development boards that I built. I built some instances of those boards. We built a sensor module. We solved a problem for an organisation in Sydney that were trying to use Raspberry Pis as Bluetooth rangefinders to measure the distance between the Raspberry Pi and a sensor, and they were finding that to be unreliable for various reasons. So we took an off-the-shelf board that was supported by Zephyr, wrote some software for Zephyr, connected that to the Raspberry Pi via USB, and provided them with a rangefinder that solved their problems. And in general, we've found that if you run into a problem with Zephyr, you've got all the tools at hand to fix it. Whereas if you run into a problem with some proprietary vendor toolkit, you've certainly got an avenue to talk to the vendor, but you don't really have any way to motivate them to help you. So now what I want to do is talk about the process of maintaining your software for an embedded device and for applying modern software practices to embedded systems. And this is one of the reasons why people find themselves outgrowing systems like Arduino, because when you are working in the Arduino IDE, there isn't really any way to manage your dependencies. You can install third-party modules pretty easily, but if you've got a conflicting set of modules for this project and a different set of versions that you want to use for that project, in the standard Arduino IDE, you don't have the power to manage that. If you're using platform.io, then you're in a slightly better situation because you do have the ability to have separate collections of modules for each program. And so one of the things that we really like about Zephyr is that it has a comprehensive test suite in the tree. It includes support for unit and integration tests. And there are templates there that you can use to start your own tests for either new drivers or for new boards or for your application logic itself. And so you've got a good foundation for encouraging you and helping you to follow the right development practices. Also, when you're working with multiple boards, you might be working on a program that you want to be able to run on several different pieces of hardware. Then there is some hooks in the Zephyr build system that will let you do that. You can basically tell it, I want you to maintain a separate build directory for each board, and that can even be a combination of boards that are defined in the Zephyr tree and boards that are defined in your own application tree. Zephyr has an inbuilt command shell. If you're familiar with the Linux command line, it's way less sophisticated, but it does let you poke around and do things. So the reason I like this is you can do things like scan for Bluetooth devices, or take readings from sensors, change the logging, reboot the system, look at the memory, configure the device to boot off a backup version of the application. Creating those shell commands is a great way to test the components of your application. I am going to speed up and perhaps skip a few sections because we are running a little bit short. The other useful thing that you'll get out of the box is a management protocol, and this is a protocol that's shared with the NbIoT operating system, and that lets me control the device either over a serial port or over Bluetooth or via one of these debug cables, and I can remotely manage the logs, copy a new version onto the software, look at the process list and resources, and even profile to get resource usage. There's also a bootloader, which you don't need to use. You can just put your raw code on the box and only have one version of it, but you can also have multiple versions there and upgrade. So you can be running off one partition essentially while you're upgrading the other one, and then you can switch between them. And you can have a fail-safe where if that upgrade doesn't work, it'll fall back to the other one. It also supports signed images. Now that may sound like an anti-freedom solution, but I see it as a security solution. Now, you don't want to have, a temperature sensor on the wall of your factory that somebody could walk up to and reprogram with their own software that happens to also record audio or something. So being able to control who updates the device, I think, is a key software feature. And finally, you can use that bootloader protocol to obtain crash dumps of any problems. So the debugging resources that we have, you can do like you would on an Arduino and print to the UART. You can use the logging subsystem to have control over modules and log levels. You can source code debug, so you can step through the code line by line under control of your workstation, and if you want to, you can even run the code on your workstation itself. And you can do a lot of this stuff over Bluetooth as well, which is really handy because that means you use these annoying cables once, and then you can stick your battery operated device up a tree and continue to upgrade it from safe ground level. And so that's where the title of this talk comes from. Linux and Zephyr sitting in a tree is what I like to do when I've got a device out in the field being tested, like this device here, which is used for feral animal management, is to have the ability for this to be a completely sealed box. It's literally waterproof. It's designed to never really ever be opened again, and I can sit at ground level or even back at my office and monitor and upgrade that. And the way I do that is I take a Raspberry Pi and I use it as an ambulance. And it could be a case of if there's Wi-Fi at the site and I'm allowed to use it, then that's fine. I'll use their Wi-Fi. If I can't, then I might send along my own Wi-Fi hotspot device, or I might use a plug-in USB 4G dongle. And there are some neat little U-turn USB connectors you can get, which will let you put your dongle here above your Raspberry Pi instead of here sticking out the end. And finally, you can use a 4G hat for your Raspberry Pi. So here's a Raspberry Pi that has a narrowband IoT 4G modem in it. And the thing I like about them is they cost way less than a standard cellular device in terms of they're about $20 for the chip. It's maybe $1 a month for the software. It's an excellent solution for ad hoc access to devices that you're going to send out into the field. I will skip the last couple of slides on on some of the drawbacks. Essentially, if you're going to use 4G, you're going to find that you're probably behind several layers of NAT and you won't be able to connect to it directly. So the options there are using some kind of VPN, and there's a whole talk that I've done on how I do that, and there will be a link for that in a couple of slides. So
thank you so much, Christopher. We're going to have to wrap up, I'm sorry, because we're just at time now.
Right.
There's a lot of really great discussion on the Venulus channel, but we don't have time for any questions, and no particular, there's been a lot of discussion, but not necessarily a lot of questions, and we're out of time in any case. So can I just say a huge thank you to you? That was really interesting. I'd love to know what feral animals it's monitoring, if you've got one moment.
Cats and dogs mostly.
Great. We can bring it over the ditch to New Zealand and monitor for possums too then. That'd be good, and stoats and such. But there's a there's a Blemmings Labs post-talk Q&A channel on Venulus. Christopher, would you mind hanging out in there a little bit, just if any questions come up afterwards? Thank you so much. And thank you, everyone. Just what's coming up next is there'll now be a break of about 35 minutes before our next talk at 3:45 AEST. Bavidim on an introduction to Vocadia. So see you all then. Thanks again so much, Chris, and we'll see you all again soon.
Cheers.
Thank you.